All right, hello. This is my lecture on signal detection theory. I'm pre-recording this lecture so that you guys can have something to do while I'm at home taking care of my wife and new baby. So hopefully everything is pretty clear in this lecture. Um, and let's get started. So the application for signal detection theory, um, we're going to pretend that you are a radar operator. And so radar operators have to decide um, what those little bleeps on their screen represent. So if you see a little signal out there, they have to decide whether they think that is a plane or something else like a flock of birds. And so when they make this decision, we can model that decision-making process using signal detection theory. So what is signal detection theory? Well, it is designed to model decisions made under uncertainty. So this uncertainty can be due to things like time pressure, where you have to make a quick decision, which is certainly true in the air traffic controller's radar operator kind of situation, or because of inherent randomness, so you might there might be lots of factors that will influence what the radar signal looks like, and those might not all be attributable to the actual object properties, maybe atmospheric noise or things like that, that could vary what the signal looks like on the screen. And the nice thing that signal detection theory does is separate out two key variables from the decision-making process. These are what we'll call D prime, which is just D with a little apostrophe after it, and it's your ability to tell the two signals apart. And we'll give you more information for what that means, but it's a basic measure of how difficult the task is. And the other variable is beta, which is your bias to choose one over the other. And it's fundamentally based on perceptual distribution. So the idea being that there is inherent randomness in our perceptual system. So let's take a really simple example here. And let's say that I played you a 20 hertz sound. So I can generate some kind of graph where if I ask you, what did that sound like to you? Most of the time you would probably be pretty accurate, right around saying 20 hertz, but some of the time you might think it was actually a deeper sound, or sometimes you might think it was a more high-pitched sound. And so we model that with just a normal distribution that has its mean, it's centered around the actual value of 20 hertz, and it has some kind of variability where, standard deviation, as they would measure it in statistics, telling you how far out might it be reasonable to say. So we'd say probably 95% of the time you would think this sound was somewhere between 18 and 22 hertz or something like that. But there is inherent variability on your perception of this. Even if we play you the exact same sound over and over again, you'll sometimes think it's lower, sometimes think it's higher. Okay, so we're going to take that idea and use it to model our signals, the things that we're trying to perceive. So from our example here, we were looking at birds and airplanes and their radar signal strength. So this signal strength dimension here is totally made up. All of this is totally made up, but we can pretend that it's real. So let's pretend that airplanes tend to have higher signal strength, somewhere around 3.5, it looks like in my graph, whereas flocks of birds tend to have lower signal strength, something around a little less than 0.3. So you notice they each get their own distribution here. So if we just look at the airplane distribution, we can see that in general, they're a little over 0.35, but sometimes the signal from the airplane is closer to 0.45, sometimes it's as low as 0.3. There's that distribution there. And similarly for birds. Sometimes it looks more like an airplane, sometimes it looks less like an airplane, like that. So the problem is there is going to be overlap between these two distributions. So in this shaded region, it's going to be hard to tell if something was a bird or a plane or Superman. Sorry. So anything in this shaded region could have been generated by the bird distribution or by the airplane distribution, and they're both somewhat equally believable. So how do we tell the two apart, and how do we, as the radar operator, make our decision about whether something is a bird or an airplane? So what we have to do is we have to pick a criterion. So what this orange bar that I laid in here basically represents is me making the decision that, okay, anytime I see any signal strength over 0.325 or whatever this number would be, I'm going to call it an airplane. And anytime I see something less than that, I'm going to call it a bird. Now, of course, I will be wrong some of the time, but we just have to pick some value that we're going to treat as our criterion, and that's what we'll use to assign our judgment. So if an incoming signal registers as 0.35 in my perception of it or on my radar screen, I'm going to call it an airplane. Anything around 0.3 or lower, I'm just going to call it a bird. And it could be an airplane, but that's something that will always be true. All right, so where you put this criterion can vary. So I put it right down the middle where they intersect, but there's nothing that special about that spot. It's a nice little symmetric place to put it, but I could shift it down here and have a more, what's called a liberal criterion. Now this is more liberal because I'm willing to call more things airplanes. So we're pretending that my task is it an airplane or not? So I'm more liberal with my criterion here because I'm willing to call anything above 0.3 an airplane. And similarly, I could have a conservative criterion where I'm not willing to call it an airplane unless it's above 0.35 or something like that. And I'm not going to call very many things airplanes. I have to be convinced of that it is an airplane before I will call it that. Okay? So now let's do some terminology here. So first let's look at the event that it is actually a plane. So that means it will come from this distribution here on the right. And we've got our criterion in here, this black line. So this was a bit of a liberal criterion, you can see, because it's to the left of their intersection. So then they have shaded here two different areas of the plane distribution. So all of the planes that are above this criterion, I will successfully call a plane. So it is a plane, and I called it a plane, and we call that a hit. Now this region down here is the portion of the plane distribution that falls below my criterion. And those we will call a miss, because it was a plane and I missed it because I said it wasn't a plane. So planes can be separated into hits and misses depending on what I respond, plane or bird. And those are the two portions of this distribution. Now similarly, we could do the same kind of thing for the distribution of birds. So if it's a bird and I call it a plane, that's what's called a false alarm, because I said plane but I was wrong. So this region here you can see is the false alarm region. So anything here comes from the bird distribution but is to the right of my criterion, so I will call it a plane, and that's a false alarm. Now this left side here, these are correct rejections. They are rejections because I'm calling them birds or not planes, because they're to the left of my criterion, and they are correct rejection because they are indeed not planes. So we have these four terms for the different events, so hits and correct rejections are good. They're when you call a plane, and when you call a not plane, not a plane. False alarms and misses are bad. It's when it was a bird, but you mistakenly called it a plane, or when it was a plane and you mistakenly called it a bird. All right? So now I'm going to map this terminology into what is more standard of signal versus noise. So normally, this has been presented as trying to hear, like let's say an audio signal embedded in noise. So if there's constantly some kind of background noise in your ears, and then occasionally they play you a beep, and you're supposed to say whether you heard the beep or not, then we're going to have a noise distribution of things you hear when there's not really anything there, and a signal distribution, which is sometimes called signal plus noise because the noise is always there. The signal distribution are when there were beeps, and so you get this when the signal is there and you say it is, it's a hit. When the signal's there and you don't say that it is, it's a miss. And when the noise is there and you say the signal was there, false alarm, noise is there, correct rejection if you say no. All right, so that makes a little, that's just to tie it into the terminology you'll usually hear, and that's why it's called signal detection theory. So it's all about detecting a signal against in a background of noise. But this situation of something versus nothing is also can be mapped onto one thing versus another thing, like we saw before. The birds would be called distractors here, and you're trying to distinguish between the two things, which is slightly different than distinguishing between something and nothing being there, but they can be modeled in the exact same way. So hopefully that wasn't more confusing. All right, but we're going to walk you through some more slides about how this actually gets applied. So, what is the effect of bias? So I talked about moving the criterion around, being more liberal or more conservative, and moving that around like that is changing your bias. So what do I mean by that? So let's start off by having our criterion right here in the middle like I started off with. And if it's right there in the middle, then half of the time you're going to say no. So I got 50% no's down here. Half of the time you're going to say yes. It is an airplane, or whatever you're trying to detect. And then I've got a rough breakdown over here of hits, misses, false alarms, correct rejections. So I said, looking at this graph of, let's just look at the airplane distribution, or the signal distribution. I said, well, I'm going to call this, all the area of that distribution to the right of the criterion, a hit. And I'll say that's roughly 80% of the distribution. And then this bit over here is roughly 20%, the misses. Those are down there. So the hits plus the misses will always add up to 100% because together they are this whole distribution of airplanes. So I could shift this criterion and have more misses and less hits, or the reverse pattern. So similarly, false alarms and correct rejections have to add up to 100% because they are the components of the noise distribution, or the birds distribution as we have it here. So I'm 20%, the false alarm rate would be all of the birds that fall on the right side of my criterion, and 80% is my correct rejection rate, everything to the left of the criterion that is a bird. So I call it a bird and it was a bird, so that's good. Now how does that change if we shift our bias, or our criterion, or bias you can say, to a more liberal criterion? So first off, you can see that I'm going to call more things airplanes, or say the signal is there more often now, because I just moved my criterion to the left, so I'm more willing to call something an airplane. All of this stuff here that I used to call a bird, I'm now going to call an airplane. So I made up some more numbers and said, that'll be, now I'm going to say, yes, the airplane was there 60% of the time. No, it was not there 40% of the time. And we can break that down to see that now, because I shifted the criterion, I have more hits, more of these airplanes I'm going to call airplanes. So that's up to 90%, and I'll have less misses. Less of these things that are airplanes will I be calling birds. Only 10% now instead of 20. But the flip side is I'm going to have more false alarms now. So you can see that the area of the bird distribution that is to the right of the criterion is now bigger. So now 30% of the time that it's a bird, I'm going to mistakenly call it an airplane. And only 70% of the time will I correctly reject a bird as not an airplane. So you can see that there are more of these yes responses than there are no responses in the same proportion of yeses and nos here. Okay, but what would happen if I took a conservative criterion? So now I am unlikely to call something an airplane. I need to be convinced of it. So we just flipped everything around here. We have 40% airplanes, 60% not airplanes. And now we can see we have fewer hits and more misses. But we're doing really good on these birds now. We correctly call something that's not an airplane 90% of the time. And we only make a mistake with our birds or our noise distribution 10% of the time. So you can see that it's a trade-off here between doing well on the signal distribution versus doing well on the noise distribution. So in the beginning, we were split down the middle. We had equal performance in both one. Or we could change it so that we're doing really good on the signal, but bad on the noise, or the reverse. Poor on the signal distribution, the airplane distribution, and good on the noise or birds distribution. And so one bias or criterion setting isn't necessarily better than the other in an objective sense. It just depends on, you might want hits more than you want correct rejections or something like that. And we can talk about how that can actually come about. So we can manipulate people's bias. So people start off with their own biases. You'll find some people who are reluctant to call things airplanes unless they know it is. And you'll find some other people who are naturally willing to call lots of things airplanes or beeps or whatever your task is. But we can actually selectively manipulate it in the laboratory by using payoffs. So if I tell you, I will give you $10 every time that something is an airplane and you successfully call it an airplane, and I'll give you $5 every time something isn't an airplane, like it's a bird, and you know that it isn't an airplane. So you can see here, it is more advantageous for you to get these ones right than to get these ones right. So as we saw before, we want to do better at the signal distribution in general than we are at the noise distribution in general. And we can do that by, would we want a more liberal criterion or a more conservative criterion? Well, we want to get more hits, and the way to get more hits is to shift this left to a liberal criterion so that more of these airplanes we're calling airplanes. And yeah, that comes at the cost of more, we're now having less correct rejections. So you can see there is less of this bird distribution that is to the left of my criterion. But because those only pay us $5, we're willing to sacrifice some of those to get more of these hits. So there are reasons why you can, so now that we have a payoff structure like this, we really could find an optimum criterion where you will make the most money by putting it somewhere here, something like that. Because if we keep pushing this criterion further left, we're only going to get a little bit more hits, but we're going to lose a lot of correct rejections. So just pushing it further and further left won't necessarily help us much, because we're already getting 90% of these airplanes. There's not many that we're missing. So it wouldn't make sense to keep pushing it much further, because then we'd lose all the correct rejections that we are getting right now. Similarly, if we swapped the payout and said correct rejections are more important than hits, then people would move their criterion over to the right. Now, the same sort of logic works in real life, without payouts, just by analyzing what the consequences of your action are. So, for instance, if we are at war, then you want to be sure that if an enemy plane enters your airspace, you scramble jets to go get it. And it's not that big a deal if you go send jets and it turns out to be birds. That's all right. That would be called a false alarm, because you thought it was a jet, but it was actually just birds. And that's not a big deal. It would be worse to get a miss when it is an airplane and yet you called it a bird. And so that kind of criterion would be a liberal criterion. We would get not many misses, which would be this part of the airplane distribution, but a fair amount of false alarms, this part of the bird distribution. And that's okay, because we just want to make sure we don't get bombed. And now, another side effect to notice from this setup is that you can never be sure that you can never fully eliminate these misses, for instance. So I told you we want to make sure an enemy plane doesn't come in without us noticing. Well, the only way to get 0 misses is to set your criterion to the absolute far left, further than you can even see here. And what you would end up doing is just call everything a plane. Whenever anything showed up on your radar screen, you would go send jets after it. And sure, you'd never miss any jets, but you would never get any correct rejections either. You would just always be sending your planes out for any bird. And likewise, you could never do the opposite and make sure that you never have false alarms. You'd have to set the criterion all the way to the right. And sure, you wouldn't have false alarms, but that's just because you would never say that anything is an airplane. So the theory is here that there is always going to be this trade-off where you're going to have some amount of misses, but that will be balanced off by all of these 4 other things. So you just have to figure out what makes the most sense. And so if you're able to quantify how much it's good to get a correct rejection versus how much it's good to get a hit, or likewise how bad it is for a miss versus how bad it is for a false alarm, then you can actually compute these things of what the optimum would be. So that's what biases look like. And now I'm going to talk about separability, the D prime I mentioned earlier. Now this is a pretty easy concept. D prime is just the distance between the means of your distributions, and it's scaled by the standard deviation. Just so all it is the size of the overlap between the 2 distributions, and it represents the overall difficulty of the task. So this one that we saw before has a decent amount of overlap, but there's a lot more overlap in this picture because the 2 distributions are closer together. And so when there's more overlap, it makes it a lot harder. you could picture if these two distributions were separated out by a lot, then we would be able to put a criterion between them that almost always, that only a little bit of this bird distribution would fall on the right side of the criterion, and only a tiny bit of the plane distribution would fall on the left side, because they'd be far enough apart that we could be really good at it, and we could get maybe 99% hits and 99% correct rejections and only have a few errors. Now over here, we're going to have a lot of errors, so you can see from this criterion that there's a lot of these false alarms here, and there's a lot of misses over here. And in fact, if the two distributions overlapped perfectly, then you'd just be screwed. You would never be able to tell them apart. You'd be at chance. And so all you could do is just pick, well, I'd prefer to call things birds, or I'd prefer to call things planes, but you'd always be doing fairly poorly. So that is a short preview of what signal detection theory is. It describes decisions made under uncertainty and does so by using those perceptual distributions. It separates out the effects of discriminability, which is how far apart the two distributions are and is represented as d prime. And it separates that out from bias, beta. So you could shift your criterion around without changing the discriminability, and likewise you could change the discriminability without changing your bias, and those will have different effects on the trade-off between your different types of errors. So it distinguishes between these different types of errors and successes: hits, false alarms, correct rejections, and misses. And that can be really advantageous to tell us what is the best strategy, especially when there are cases where the different outcomes are differently weighted, where a miss would be much more disastrous than a false alarm. And so this has been a very successful paradigm that's been used to study all kinds of different things, like how real radar operators operate, as well as a lot of psychology laboratory type experiments, like how good are you at detecting a tone, or finding a stimulus, or sensing a bright light, or all kinds of stuff like that. And it does a good job of factoring out each subject's individual biases and separating that effect from the discriminability, because we usually don't care that much about whether someone is more likely to say, yes, I saw the light, than no, I didn't. What we want to know more about is how good are they at actually seeing the light. And so signal detection theory has proved really successful at being able to identify, to separate out those two effects. And it's pretty cool. And so we've got a paper which I'm going to post online, where some researchers use signal detection theory to dispute some important findings that had been in the field for a while, and it's a pretty interesting conclusion. It's a cool outcome about how discriminability and bias can be confused if you don't separate them out like this. And then I'm also going to have you guys, so I'll post that online for you guys to read, and you'll answer some JIT questions about it. And then I'm also going to have you go through the signal detection theory ZAPs, which are online. There's 2 of them, and they should patch up any of the holes that I left in this presentation. I'll also post this slideshow in case you want to look at it without my annoying voice over it the whole time. So I'll be back in a week, and look forward to seeing you guys. Hope you do well with this material. It can be a bit confusing, but it's really powerful stuff, and if you can get an understanding of it, it can help a lot. All right, good luck. Email me any questions. Thank you.